This is a video for AQA Discrete Mathematics, Binary Operations section 1.3, where we're going to be looking at identity elements and inverses. Well, I'd like you to start by just having a look at this Cayley table, which shows addition modulo 5 on the set of numbers 0, 1, 2, 3 and 4. And in particular, I'd like you to look at the first row and the first column and say, what have we got that's significant about that? And I'm sure then that you can see that the first row is just a repeat of the headers, so it basically is showing that there's no change from the elements, and likewise in the first column. So in other words, we can say that 0 plus a and a plus 0 modulo 5 are both equal to a, so the element itself doesn't change, or 0 is not going to change it. So if that's the case, we say that 0 is the identity element for this operation. Now in general, we often use E as the symbol for the identity element. So you can see in this table here that E is not making any change to any of the elements E, B, C or D. In other words, we have that E combined with whatever the combination is, an element, let's call it A for example, then that will be equal to A combined with E is equal to A. So that's our general statement, and where in this particular case our element A is one of the set. So I'm using A there as a general element as opposed to one of the particular ones in the set. So here we've got an operation that we've already studied. This is multiplication on the set 1, -1, I and -I, and you can see there that the identity element is equal to 1. Here's another example. Just like to look at that and say, which do you think is the identity element in this case? I think you'll see that the row there for B and the column for B is the one which doesn't change, so therefore E, the identity element in this particular case, is B. Well, once we've got the idea of an identity element, we can go on and discuss what we mean by an inverse. So let's look at this table here. So it's asking us to say, well, can we find x such that x star 2 is equal to 0? Well, obviously we can look at the table here, and we can see that 2 combined with 3 gives us 0, so that's our identity element. And also, if we looked at the other way around, 3 combined with 2 is also the identity element. So we can say that 3 star 2 is the same as 2 star 3, which is equal to the identity element E, which in this particular case is 0. Now that means that 3 is what we call the inverse of 2. So we can say that 2 inverse, if we wanted to use that notation, is equal to 3. Because when you combine something with its inverse, you get the identity element. So in general, we say that A combined with its inverse element, A inverse, gives us E. So every element has an inverse element, so if A has an inverse A inverse, then we can say that A inverse is A inverse A is equal to E, the identity. For us to find the inverse of I, so remember that the identity element for this particular one is equal to 1, so we're just really saying what element is combined with I to give us 1, and we can see that if we look at I then we need to combine it with minus I to get the value 1. So the inverse of I is equal to negative I. So inverse of I is equal to negative I, and that's because I multiplied by negative I is equal to 1. And also we could do it the other way around, so negative I multiplied by I is the same. Well, in this one, remember we had the identity element was equal to B. So let's look at A inverse. We can see that A inverse is equal to A, because A combined with A gives us the identity element B. So this is what we say here is that therefore A is what we call self-inverse. So it is its own inverse. Now you're familiar with self-inverse operations. For example, a reflection is a self-inverse operation, so that if you looked at a matrix which does a reflection and multiply by itself, which will then you would get back to the identity matrix. C, if we look at C, then you can see that that has an inverse of D. So we can say that C inverse is equal to D, because C combined with D is the same as D combined with C is equal to the identity element E. So C and D are inverses of each other. Well, it's not just these new things that we've been looking at that are sets and operations which have identities and inverses. You may not have thought about this before, but your normal arithmetic has an identity and inverse for each of the operations. So for multiplication in particular, the identity would be equal to 1, and then the inverse of 3 is 1/3, and that because 3 multiplied by 1/3 is equal to 1, and 1/3 multiplied by 3 also, so you must check the other way around. And now let's go on and look at a binary operation on a set of matrices. So here we have a set of 4 2x2 matrices, which obviously, if you think about it, are transformation matrices. And we can ask about those. Is there an identity element? And then construct a Cayley table so we can find the inverses of each element. Well, you'll be familiar with the identity element for matrices as being 1, 0, 0, 1. So the identity element is D, so that's the matrix 1, 0, 0, 1. You may want to think about what each of these matrices performs in terms of a transformation. If you look at where the unit vectors have gone to, then in A, I dashed is 0, 1, and J dashed is -1, 0. So that's a rotation of 90 degrees in an anti-clockwise or positive direction. -1, 0, 0, -1 in B, that gives us I dashed down here. Sorry, I beg your pardon, that's J dashed is there, and I dashed to the left, and that's a rotation of 180 degrees. So this is a 180 degree rotation. And finally C, I dash at 0, -1, and J dashed at 1, 0, and that one is a 90 degree rotation in clockwise direction about the origin. Well, in asking to construct a Cayley table for the set, then we know that D is the identity, and therefore we can fill in the table for the row for D, A, B, C and D, and for the column for D, A, B, C and D. To work out the others, however, we're going to have to either think about the transformations themselves or do some matrix multiplication. Well, for example, we know that these are rotations about the origin, and when we combine two rotations, it's quite straightforward. So for AA, for example, 90 degrees followed by another 90 degree rotation is going to produce a 180 degree rotation. So we can see from that that A times A must be equal to B, and also, for example, then that A times C, where we do a 90 degree rotation which is anti-clockwise followed by a 90 degree rotation clockwise, must get us to being D, and vice versa. So we can see that AC must be the same as CA, which is equal to the identity D. The other way of considering these, though, is to look at the matrix multiplication, so I'll look at some of that now. If we multiply together A with itself, then indeed the matrix that we get is -1, 0, 0 and -1. So that is equal to B, which confirms what we'd said already, considering the transformations. Two 90 degree rotations about the origin is going to produce a 180 degree rotation. If we look at A and B, then here we get 0, 1, -1 and 0, which is C. And again, thinking about that, A and B combined, so we've got a 90 degree rotation and a 180 degree rotation in an anti-clockwise direction, is going to combine to 270 degrees about the origin, which is the same as going 90 degrees in the other direction, which is C. And also, if we do BA, we get the same, which is C. In general, remember that with matrix multiplication, it's not going to be the case that it's commutative. Here we've got AB is equal to BA, so commutativity is true for this particular multiplication here, but in general it's not going to be the case. And finally, BB gives us the identity element, which of course you would expect because we've got 280 degree rotations. Well, if we add those to our Cayley table, we'd found that A multiplied by A, or A followed by A, gave us B. AB and BA both gave us C, and B followed by B was D. Now once we've done that much, then because we know that the Cayley table has got to have the elements in each row and each column, we can fill in the rest. That must be D, this one here must be A, and then we have along here D, A, and finally B. And then once we've got the table showing all the combinations, then we can think about what are the inverses of each element. So remember that the inverse is the thing that we multiply together to give the identity. So we can locate the identity here on our Cayley table, so that we can see that A inverse is equal to C, and C inverse is equal to A. B is what we call self-inverse, so B inverse equals B, and of course the identity element is always its own inverse. Well, that concludes this video on identities and inverses, and indeed is the last in the series of videos about binary operations.